Welcome to another session of digital circuits. In this session, we'll see how any function can be implemented by the Boolean gates, and we'll also see how a Boolean function can be implemented by using the universal gates. Any digital system can be implemented by using universal gates. So we'll first start with the implementation of basic gates using universal gates. First, the NOT gate and its implementation using the NAND gate. NOT, the output Boolean expression for the NOT is A bar if its input is A. A can be rewritten as A and A based on the Boolean theorem. So A bar will become A and A the whole bar. So what we need is an AND gate with two inputs as A. So this is how a NOT can be implemented using a NAND. Next, implementation of AND using NAND. The output Boolean expression for AND is A and B. A and B can be written as A and B, the whole double bar, using the De Morgan's laws. So what can we do? We can have an AND gate, and the output of the NAND gate can be connected to another single input NAND gate. The implementation is here. Next is OR using NAND. The output expression of the OR is A plus B. Call the De Morgan's law. A plus B is equal to A bar, B bar, the whole bar. So what do we need now? An AND gate whose inputs are A bar and B bar. Implementation is here. Having seen the implementation of basic gates using the universal gates, we'll next see how functions can be realized using gates. The first example which has been taken is implementation of f is equal to ab plus ab bar. Here the realization is asked, but realization using a typical gate is not specified. So you can make use of any gate. Look at the expression again. F is equal to AB plus AB bar. The first term is a product term, so an AND gate or an AND gate can be made use of. The second term is again a product term, so again you can make use of an AND gate, and the two product terms should be OR. So now this is the complete realization, but now I'll do it on a step-by-step basis. The first term is AB. AB is realized using the first AND gate. The second term is AB bar. To implement AB bar, an AND gate is again taken. One input is A and the other input is the inverted form of B, which is B bar. The last expression is AB plus AB bar. So the last gate which is needed is an OR gate. So the outputs from both the AND gates can be fed as the inputs to the OR gate, and the output is the required expression of F. Based on the same explanation, the implementation of F is equal to ABC, ABC bar, A bar, B, C bar is given. So three AND gates, the required NOT gates, and a final OR gate. So in the previous slides, it was the implementation of SOP expressions. SOP expressions are sum of products. Now it's the POS expression, product of sums. So A plus B is a sum, A plus B bar is a sum, and the final expression for F is the product of A plus B and A plus B bar. So it's obvious, to implement the first term A plus B, you need an OR gate. To implement the second term A plus B bar, you need another OR gate. And for the final expression F, you need an AND gate to AND A plus B and A plus B bar. So the second example is the implement of a three-term expression. F is equal to A plus. The next example is the implementation of the given function. The first OR term or the first sum term is A plus B, which is implemented by using this OR gate. The second term is A bar plus B bar plus C. So the second OR gate has its inputs as A bar, B bar, and C. Third OR gate has its inputs as A, B bar, and C. And finally, the AND gate, which ANDs all the sum terms. So, the third type of problem is implementation using a specific gates. Normally, implementation using an universal gates is desired. So, we'll see how any expression can be implemented by using a NAND gate. The example which has been taken is f of a comma b comma c comma d comma e. Look, it is a 5 variable function is equal to a plus b bar plus c into d bar plus b e bar using only NAND. So the step 1 is implement it using any gate as we had done in the previous examples. A quick recap again on how an OR and an AND can be constructed by using only NAND. Look at the first expression, an OR. A plus B is the output of this OR. Consider the De Morgan's theorem. A plus B is equal to A bar into B bar, the whole bar. So take a NAND. Inputs to the NAND should be A bar, B bar. So both the terms or both the figures are the same. An OR can be constructed as a NAND gate with a bubble at the output and two bubbles at the input. Similarly, an AND can be constructed as an OR with two bubbles at the input and a bubble at the output. So the step 2 in the implementation using only AND gates. Step 2, convert AND gate into NAND gate. But how? A bubble is deliberately introduced at the output of the AND gate. And the step 2 in step 2 again, to compensate for the bubble, the input of the next gate is also introduced with a bubble. Step 3, look for the gates. If a gate has one input with a bubble, the other input is also introduced with a bubble, right? In order to compensate for the bubble, the output of the preceding gate is introduced with a bubble or complement the literal. Now look at this figure. The two bubbles which have been marked do not have a preceding gate. Step 4. If an OR gate does not have a bubble at either of the inputs, bubbles are introduced and are appropriately compensated. Step 4. If an OR gate does not have bubbles at either of the inputs, bubbles are introduced and are appropriately compensated. So consider this OR gate. In the previous slide, there were no bubbles at the input. So bubbles are deliberately introduced. What do you mean by appropriately compensating? When you look at the previous slide, you can see that the inputs to this OR gate are B bar and C. Since bubbles are deliberately introduced, we invert the two literals and they now become B and C bar. Step 5, utilization of De Morgan's law. A bar plus B bar is equal to AB the whole bar. So if an OR gate is there with two of its inputs inverted, that can be conveniently replaced with an NAND gate. So in this figure, three OR gates are replaced with NAND gates. The final circuit thus has only NAND gates. Implementation of any circuit can thus be done using only NOR gates. Use the De Morgan's law, make the simplification, and the circuit will consist of only NOR gates. We come to the end of this session. Hope you would have enjoyed it. Thank you.